Good morning, everyone. My name is Aman and welcome to this GCSE Chemistry session for the MyTutor online school. Today's session we'll be looking at pollutants and the reactivity series. I hope you all had a lovely weekend and this is the first session or the first webinar for this week. It will last 1 hour from 9:45 until 10:45 and as usual, if you have any questions at all, then you can just pop them into the chat or the Q&A function. If you haven't met me before, I've led all the GCSE chemistry sessions for the MyTutor online school. And as I said, my name is Aman. I study medicine at King's College London and I've done over 200 lessons with MyTutor. So let's get started. Today's learning objectives are to know and explain the harms of atmospheric pollutants. So this is the last learning objective for the topic of the Earth's atmosphere. And then we'll be doing a little snippet on the reactivity series and displacement reactions. So displacement reactions we'll be looking at tomorrow. Today we'll be looking at how the reactivity series was formed and how we can test for that by using the reactions of metals with water, steam and acid. So the reason we're doing this little snippet is because I know some people were asking a couple of weeks ago about the reactivity series. So I thought we'd include this. So today and Wednesday, we'll be looking at that. So before we go into the new content for today, I thought we'd do a quiz testing Friday's content on global warming. So if you were here on Friday, you'll know that we looked at global warming in quite a lot of detail. So we looked at the greenhouse gases, the greenhouse effect, and the impacts of global warming and what we can do to try and reduce it. So I've got a quick quiz then testing that. So if you go to menti.com and type in the code 278148, you should be able to join. So I'll give you a couple of moments to do that. Great, so I can see that one person has joined, so that means the link's working. So I'll just wait for some more of you to join that quiz. And if you've got any questions at all about last week's content, then feel free to ask them. If you haven't used Menti before, it's completely free to use. You don't need to make an account, so you should just be able to go to menti.com and pop in that code to be able to do the questions. And as usual, the faster you answer the questions, the more points you get. So usually it's a bit competitive. And if you don't want to join the quiz, you can always answer the questions on the Q&A or the chat. So it's completely up to you. So I'll just wait a few more moments and then we'll start the quiz. Okay, I think we'll start the quiz then. If you haven't already joined, you should be able to join partway through, but I'm going to start it now. So the first question should be coming up on the screen. Which of these is not a greenhouse gas? Which of these is not a greenhouse gas? So it's a multiple choice question. Is it carbon dioxide, methane, nitrogen dioxide or ozone? The key part of the question is it's not a greenhouse gas. So that means 3 of them are greenhouse gases, 1 of them isn't. So you need to select the one that isn't a greenhouse gas. So the answer is nitrogen dioxide, so excellent. No one put carbon dioxide, which I'm really pleased with. So that's one of the main greenhouse gases, so is methane. Ozone is a greenhouse gas. So if you were here on Friday, you'll know that ozone is O3. So oxygen usually goes around as O2. Ozone, O3, is a greenhouse gas, and it's also a layer in the atmosphere known as the ozone layer. But yes, it is a greenhouse gas. So the one that isn't is nitrogen dioxide. The name for the greenhouse gas that starts with nitrogen is known as nitrous oxide, which is N2O. So nitrogen dioxide is NO2, which isn't a greenhouse gas, but nitrous oxide, N2O, is a greenhouse gas. So well done to the people that got that correct. Okay, so the next question should be coming up. Which type of energy do greenhouse gases absorb? So this is a question directly about the greenhouse effect. So if you remember the diagram that we drew, which type of energy do greenhouse gases absorb? So is it solar, ultraviolet light, visible light, or infrared? Okay, so the answer is infrared energy, and that's because solar energy comes from the sun. And you'll remember the Earth absorbs most of that solar energy, about 50%. It will then reflect it once it's been absorbed as infrared, and that should go into the atmosphere, but the greenhouse gases will absorb that infrared energy and re-emit it back down to the Earth and in all directions. So essentially the energy that should be going back into space to cool the Earth down isn't, because the greenhouse gases are absorbing it and re-emitting it back down to the Earth. Great, so well done. Which of these increase methane production? Which of these increase methane production? So you remember methane is a greenhouse gas. Is it deforestation, landfill waste decomposition, burning fossil fuels, or bacteria carrying out aerobic digestion in swamps? So this one's a bit tricky, but have a go. Okay, so everyone's voted. So the answer is landfill waste decomposition. Okay, so deforestation, no one put that. But deforestation means the cutting down of trees, and the reason that that does increase global warming and greenhouse gases is because it releases carbon dioxide. So you remember we need trees to take in carbon dioxide. The answer is landfill waste decomposition, and the reason for that is that when we deposit waste into landfill, anaerobic bacteria, so anaerobic means without oxygen, so they carry out digestion of organic material. Organic material just means usually made of carbon. They carry out digestion of that anaerobically, so without oxygen, and that releases methane. And critically, it's anaerobic digestion that does that. Burning fossil fuels does not release methane, that releases carbon dioxide. So you remember the classic combustion reactions that we do when we react our hydrocarbons with oxygen, we produce carbon dioxide and water if it's complete combustion, and if it's not, we produce some type of carbon compound. And this one again is partially correct, but the word that's wrong is aerobic. It should be anaerobic digestion. So bacteria do carry out digestion in swamps, and that does release methane, but specifically it has to be anaerobic, because aerobic digestion, which means with oxygen, does not release methane. Okay, great. So the next question should be coming onto the screen now. Which of these is not an impact of global warming? Which of these is not an impact of global warming? So the key part of the question again is not. So 3 of the answers are correct and 1 is wrong, and it's the wrong one that you want to click. So does global warming cause rising sea levels? Does it cause ecosystems to change? Does it cause calmer weather, or does it cause more droughts? Which of these is incorrect? Great. Yep, so the weather will be more stormy and more erratic. So we expect kind of some people will get droughts, some people will get floods. So although there will be more droughts, it's not just more droughts, it's more droughts and floods. As well as this, ecosystems are changing, so habitats are changing as well. We're losing some animals that are going extinct, and rising sea levels is an impact of global warming. So these 3 are all impacts of global warming, whereas calmer weather is not an impact of global warming. Okay, next question's coming up on the screen now. Why does global warming cause sea levels to rise? So why does global warming cause sea levels to rise? Is it because there's less melting of ice caps? Is it because the oceans expand? Is it because there's more rain? Or is it because there are less droughts? So which of those cause sea levels to rise? And I haven't put the typical answer in there. So it's one of the other answers that we went through last week. Great, yep, most of you got that. It's because oceans expand, so excellent. So there's actually more melting of ice caps. So that's the traditional answer for why sea levels rise. It's because glaciers and ice caps are melting, which then when they melt, that leads to water entering the oceans, which causes the oceans and sea levels to rise. The other thing is that as it gets hotter, liquids tend to expand, specifically water. So the oceans will expand, which again causes sea levels to rise. There is more rain, but that doesn't directly mean that the sea levels rise. So that doesn't affect the sea levels. And again, droughts is to do with dry weather, so that wouldn't affect the sea levels. Great, well done. So we're going to see a leaderboard now. Don't leave the quiz just yet, because there is another question. It's just not part of the quiz. So well done to this person here for winning. Excellent. I hope you guys enjoyed that quiz. So the next question then is, how can we reduce global warming? So you should just be able to type in some answers. I think everyone's limited to 2 answers. So can anyone remember the ways in which we can reduce global warming? So I had a slide up on Friday where we went through a lot of lists. Great. So someone's saying flood defences and irrigation systems. So that's how to mitigate the effects of global warming. So specifically, if global warming's happening, what we can do is we can put flood defences in to stop those all the rainfall basically. An irrigation system is if there's a drought, we can provide water to our plants. Good. Yep, we can recycle. Deforestation. So we want to plant trees to stop deforestation. We want to reduce carbon dioxide emissions, burn less fossil fuels. Excellent. Yep. Really good answers, everyone. Using biofuels. Yep. I really like that. Vegan diet. Yep. Excellent. Good. Well done. So this is just a recap of how we can reduce it. Someone's saying they've just joined the session. No, we're just doing a quiz, basically going over what we covered last week. So at the moment, we're just thinking of ways we can reduce global warming. If anyone else wants to answer, then they can. I'll just wait a couple more moments. Great. Yeah, electric cars are a really good idea as well. So remember, there are some disadvantages with electric cars as well, though. But yeah, they do burn less fossil fuels than traditional diesel or petrol cars. Excellent. Okay, great. So I hope you all enjoyed the quiz. So let's go back to today's session then. So I will close the quiz now. So as we said, today we're going to look at atmospheric pollutants. Then we'll do some exam questions, kind of summarising the Earth's atmosphere and that topic, and then we'll go into the reactivity series. So let's start with atmospheric pollutants then. And before we go into this, I just want to stress that it's really important you don't get confused between the greenhouse gases and the atmospheric pollutants because they are slightly different. So you'll remember we went through 6 greenhouse gases last week, including carbon dioxide, methane, ozone, nitrous oxides, the industrial gases, and water vapour. So they're the 6 that we went through. The atmospheric pollutants are slightly different. So the greenhouse gases will undergo the greenhouse effect and cause global warming. Atmospheric pollutants, although one of them is a greenhouse gas, the others are not. So they do not contribute to the greenhouse effect. Instead, they cause other things that happen to the atmosphere, and that's what we're going to be looking at today. So these pollutants come from burning fuels in complete and incomplete combustion. So we've looked at combustion lots and lots over the past couple of weeks, and today we're just going to kind of consolidate that and bring it all together. So the main pollutant that is also a greenhouse gas is carbon dioxide. So we know that when we burn hydrocarbons or fuels and burn them with oxygen, so when I say burn, I mean kind of reacting them with oxygen, we produce carbon dioxide and water. And carbon dioxide is an atmospheric pollutant. On the next slide, we'll talk about what it does to the atmosphere, but that is how that atmospheric pollutant is produced. The second atmospheric pollutant is carbon monoxide, and you may remember that carbon monoxide and carbon particles, so both of these, are produced when we undergo incomplete combustion. And remember, incomplete combustion essentially means that there's not enough oxygen. So if we had lots and lots of oxygen, carbon dioxide would be produced, but without lots of oxygen, we either get carbon monoxide and water or just carbon particles and water. And again, we'll be looking at the effects of carbon monoxide, carbon and carbon dioxide on the next slide. So they're the 3 atmospheric pollutants that we've looked at before or we know about. There are 2 new ones today, and the 2 new ones are sulfur dioxide and nitrogen oxides. So again, these are not greenhouse gases, these are atmospheric pollutants. You'll remember that it's nitrous oxide that is a greenhouse gas. Nitrous oxide is N2O. Nitrogen oxides are known as NOx. And the X just means that that number could be anything. It could be 2, it could be 3. So nitrogen dioxide, for example, is an atmospheric pollutant, and that would be NO2. But because there are lots of different nitrogen oxides, we put NOx to mean that we don't know how many oxygens could be in that particle, but all of them are atmospheric pollutants. So how do we produce sulfur dioxide? Well, a lot of fuels contain sulfur impurities. So a lot of fuels, petrol, diesel, and hydrocarbons contain sulfur impurities. And what impurity means is that instead of just being made of hydrogen and carbon, they tend to contain a bit of sulfur in them. And it's that sulfur that reacts with the oxygen when we burn these fuels to produce sulfur dioxide, which is SO2, so sulfur dioxide. So when we burn our fuels, because there are some sulfur particles in there, they will react with the oxygen to produce sulfur dioxide, and that is an atmospheric pollutant. Again, we'll look at its effects on the next slide. Someone's asking about carbon monoxide killing you. Yes, it can, and we'll look at why that is on the next slide. So nitrogen oxides, that's the final atmospheric pollutant that we need to know about. So you'll remember when we've looked at nitrogen before, I've always said it's an unreactive gas, and it is. And that's why it's been allowed to build up in the atmosphere. So hopefully, if you were here last week, you know that in the modern atmosphere, what percentage is nitrogen? Does anyone remember what percentage in the modern atmosphere, so in our air right now, how much of it is nitrogen? Excellent, 78%, very good. So 78% is nitrogen. So nitrogen in itself is unreactive and not harmful to us at all. But what happens is when we burn our fuels, nitrogen in the engines of cars, in trains, and all of these vehicles, there's a lot of energy there. It's very high temperature. So that nitrogen can react with oxygen, because remember, we're burning fuels. So that nitrogen in those very high temperatures in engines can react with oxygen to produce nitrogen oxides. So this is a unique situation where nitrogen will react with oxygen, and it's when it's specifically exposed to very high temperatures in engines. So nitrogen itself is not harmful, but nitrogen oxides are, and we'll think about that on the next slide. Are there any questions about those 5 pollutants? So carbon dioxide, carbon monoxide, carbon particles, sulfur dioxide, and the nitrogen oxides. Again, very different from the greenhouse gases, but we still need to know about them as pollutants. Okay, so no one's asking any questions about that. So let's go on to this slide. So this is a diagram that I made over the weekend to summarize what all of these pollutants do. And it's one way that helped me to remember what these pollutants do when I was revising for my GCSE Chemistry exams. So I thought we'd start off with the carbon particles. So carbon particles, carbon dioxide and carbon monoxide, just because we've looked at those before. And then we'll look at nitrogen oxides and sulfur dioxide. So we'll go through it slowly. I showed you a very similar diagram last week when we were looking at positive and negative ions. So I've said before, I find mind maps helpful, or flowcharts helpful. They're not going to be helpful for everyone, but I just thought I'd show you just in case some people do find them helpful. And as usual, feel free to screenshot it if you would like. So let's start with carbon dioxide. So as I said, carbon dioxide is produced by complete combustion. And the only harmful effect of carbon dioxide is global warming. So I'm not going to go into that in too much detail because we looked at global warming last Friday. So it is an atmospheric pollutant, but for the pure purpose that it causes global warming. So the other greenhouse gases only really carry out the greenhouse effect, but carbon dioxide is the most prominent atmospheric pollutant. And the reason it's an atmospheric pollutant is because it causes global warming. Any questions about that? Someone's just asking me to go back to the previous slide. Yes, I will go back to the previous slide. Yep, they are all mixed with oxygen, so some amounts of oxygen, and it's because it happens when we undergo complete or incomplete combustion. Okay, great. Let's look at carbon monoxide. So again, in the dark blue, that means it's produced by incomplete combustion. So this whole diagram, the red are the atmospheric pollutants. In the dark blue, it's how that pollutant is formed. And then in the green and the purple is about what the effects are of that pollutant. So carbon monoxide formed by incomplete combustion. Remember, that means less oxygen. And what does it do? Well, it's toxic to our red blood cells. So the red blood cells in our body carry oxygen and they are vital. We need that oxygen for all the cells in our body. And it's those red blood cells that carry that oxygen to all the other cells. So to our brain, to all our muscles, we need that oxygen. But when there's carbon monoxide in the atmosphere and we breathe it in, what happens is that carbon monoxide essentially competes with the oxygen that the red blood cells are carrying and actually overpowers that oxygen. And so what happens is that the oxygen in the red blood cells reduces, and instead the red blood cells start carrying carbon monoxide. And that's dangerous because we need oxygen in our body. All our cells need oxygen and we can't survive without that oxygen. So if our red blood cells are carrying carbon monoxide instead of oxygen, it means that our body starts to suffer. So this used to be a big problem in olden day houses where they had boilers that used to produce carbon monoxide. That's all changed now. There are very few houses that have carbon monoxide boilers, and in fact most houses now have carbon monoxide detectors, and that keeps the carbon monoxide levels low, so that no one can get ill from it, because as someone said, can it kill you? Yes, it can. If you're exposed to carbon monoxide for a long enough time, your oxygen carrying capacity of red blood cells reduces so much that your cells don't get enough oxygen, and that can kill you. But usually it's a very slow process, and it does get caught most times, so that we can reverse it. So any question about carbon monoxide at all? So I think we have looked at this before, about the effects of it when we looked at combustion, but as I said, this is a summary diagram of all the atmospheric pollutants. Okay, the other carbon atmospheric pollutant is just carbon particles themselves. So remember, again, in incomplete combustion, specifically in diesel engines usually, carbon particles are produced. So again, you're thinking about soot. So they tend to be quite black particles. So they're not gases themselves. They tend to be kind of very fine particles. So soot is made of carbon. And they have two effects, these carbon particles. The first effect is that they are irritant to lungs. So remember I said they're not really gases, they are particles. And so if we inhale those particles, so if we breathe them in, they can be irritant to the lungs and can actually increase the chances of lung cancer occurring. Someone's asking for the difference between carbon dioxide and carbon monoxide. Yep, so good question. So carbon dioxide is CO2, so there's two oxygens there. And this is not harmful to us. It's harmful to the atmosphere, but it's not harmful to us. Carbon monoxide is one carbon bound to one oxygen, and that is harmful to the red blood cells in our body. And then carbon is just carbon with no oxygen. So it's all to do with how much oxygen is bound to that carbon. So irritant to the lungs, because they are particles. If we breathe them in, the lungs don't like it, and they can cause lung cancer. The second thing is global dimming. So does anyone know what global dimming is? Any ideas what global dimming is? Yeah, pretty much. So someone has said that it's when light is blocked from entering the atmosphere and the world becomes dimmer. Yeah, really good answers. Great. So what I thought we'd do is I'll just show you this diagram again from last week. So remember when we looked at the greenhouse effect, we filled in this diagram to talk about that. So this time we'll fill it in for global dimming. So what usually happens is that sunlight from the sun comes to the earth. So remember that's solar energy. So solar energy comes from the sun to heat the earth up. And then the heat will absorb that energy, the earth, sorry, will absorb that energy and re-emit it as infrared. So these red lines are infrared, and that should go into space. So this infrared energy should go into space. But what usually happens is if there are greenhouse gases in the atmosphere, so remember I drew them as particles like this last week, so let's just say these are greenhouse gases, they absorb it, and when they absorb that infrared radiation, they then emit it in all directions. So it becomes emitted, so it'll go down to Earth, some will go up to space, but most of it does go down to Earth, so it gets emitted in all directions. And essentially that's not what's supposed to happen, because the Earth wants to emit that infrared radiation into space to cool itself down. So this is global warming and the greenhouse effect, and that's what's happening when the greenhouse gases absorb that infrared radiation. But global dimming is slightly different. So in global dimming, what's happening is we still have these particles, but specifically they're soot particles or carbon particles over here, and they interfere on this part of the diagram. So when the sunlight comes to the Earth, instead of it being emitted down to the Earth so that the Earth can absorb that solar energy, these carbon particles or soot particles absorb that solar energy and then re-emit it back into space. So it goes back into space. So what happens is the Earth cannot absorb a lot of that solar energy. So essentially it's all about the Earth becoming dimmer, as someone said, and having less light because of these soot particles absorbing that solar energy and re-emitting them back into space. So that's what global dimming is. So it interferes on this part of the diagram. Global warming is over here. So they're kind of direct opposites of each other. Any questions on that? So someone said light is blocked from entering the atmosphere. Pretty much, yep, that's what's happening. So any solar energy that's coming in, the carbon particles will absorb and re-emit back into the atmosphere, so it never reaches the Earth. Great, okay, so let's go back to our diagram. So as I said, carbon is irritant to the lungs and causes lung cancer, but it also causes global dimming, which is another big impact. Okay, so does global dimming affect cooling, and global warming is increasing? Yep, so there's big kind of scientific disputes about what happens between global dimming and global warming. What they think is happening at the moment is that the effects of global warming overpower the effects of global dimming. So there are more greenhouse gases than there are carbon particles. So global dimming is occurring, but there's more global warming occurring. So global warming almost overpowers the effect of global dimming. But that doesn't mean we're getting less sunlight, we are. So they've had a look over a number of years, the amount of sunlight reaching the Earth is actually less than it used to be. So global dimming definitely is taking place, but so is global warming, and global warming is taking place at an increased rate. Okay, so we've looked at all the carbon atmospheric pollutants. The next atmospheric pollutant then we'll look at is sulfur dioxide. So you remember I said that sulfur dioxide is produced because there are sulfur impurities in fuels. And so when we burn these fuels, any sulfur impurities there will react with the oxygen to produce sulfur dioxide. So it's oxidation of sulfur impurities in fossil fuels. So oxidation, oxygen reacting with the sulfur impurities in the fossil fuels to produce sulfur dioxide. And the major impact of sulfur dioxide is acid rain. Now, I'm sure a lot of you have heard what acid rain is. So we'll have a think about that today and what that is. So acid rain is produced when sulfur dioxide in the atmosphere, so remember it's produced because of the burning of fossil fuels, reacts with water. So when it rains, the sulfur dioxide will essentially dissolve in that water to produce sulfuric acid. So sulfuric acid. So when sulfuric acid is produced, the rain becomes acidic. So we call that acid rain. So it's sulfur dioxide in the atmosphere dissolving in the rainwater to produce sulfuric acid. And that sulfuric acid is obviously then in that rain. So we call that acid rain. And acid rain has three main impacts. The first one is that it damages trees and plants. So specifically what happens is that the leaves of trees and plants have a waxy layer on them. And that acidic acid rain will interfere with that waxy layer. And it means that the leaves of trees and plants cannot absorb minerals, so they can die. So our trees and plants need minerals to survive, and they get them from the soil. But if the waxy layer of trees and plants are damaged by the acidic, so sulfuric acid in the rain, it means that they can't absorb those minerals. Someone's asking about why nitrogen oxides also lead to acid rain. I'll come on to that when we talk about nitrogen oxides. Yep, so someone's talking about limestone. So that's over here, we'll talk about that in a second. So that's why it damages trees. It's to do with the waxy layer of leaves and plants being damaged by the sulfuric acid in the acid rain. The second thing is we've already talked about it kind of killing plants, but it also kills animals and plants for the reason that if we think about aquatic life, so aquatic life means fish and animals in our lakes and our rivers. When the acid rain falls, it will fall into these lakes and rivers and will make the water acidic. And fish and animals in the water cannot survive with acidic water. So they need kind of more purified water. They cannot survive in acidic water, and that's what kills them. And it's the same with aquatic plants as well. And then the third reason is that it damages limestone buildings and metallic structures. And so metallic structures and limestone buildings are corroded. Corroded or eroded, so basically broken down. So limestone buildings are made of calcium carbonate, and the sulfuric acid will react with that calcium carbonate and break it down. And again, we're going to look at how acids react with metals today. But acids do react with metals and they produce different products, but they essentially break down those metals. So that's what sulfur dioxide does. So acid rain is mainly what's produced from sulfur dioxide, and then that has many effects on the atmosphere. So the final one then is nitrogen oxides. And remember, I wrote that as NOx because that oxygen could be 2, it could be 3, you could have many different oxygens bound to that nitrogen. So remember, it's produced at high temperatures in vehicle engines. So remember, nitrogen is unreactive, but at high temperatures in vehicle engines, it will react to produce nitrogen oxide. So someone is asking me, does global dimming contribute to less sunlight and colder temperatures? Yes, yeah, essentially it does. Well done. So nitrogen oxides then, so first of all, they do cause acid rain. And again, and that is because nitrogen oxides, when they react with water or dissolve in water, they produce nitric acid. So that is why there's acidified rain, so nitric acid. So you'll remember the sulfuric acid is H2SO4, nitric acid is HNO3. So it produces nitric acid when it dissolves in water. And that's why we get acid rain. I've not written the effects of acid rain because they're up here, so you can look at those. It's exactly the same as sulfuric acid. The difference with nitrogen oxides are that they are also toxic to humans. Specifically, they trigger asthma attacks. So they can be irritant to our lungs, not because they're particles, they are gases, but if we inhale them, they can trigger asthma attacks in people that are prone to asthma or have asthma, because they can be one of the particles that are irritant to them or cause their asthma attacks. So that's the 5 atmospheric pollutants that we need to know about. So you need to know how they're produced, which is in the dark blue, and then what the effects are. The main questions I've seen tend to be kind of multiple choice, asking you what are the effects of sulfur dioxide, and then you have to kind of almost join up sulfur dioxide with acid rain. And same with carbon, joining up with global dimming or irritant to the lungs. Any questions on those atmospheric pollutants? Because that's kind of the last topic that we had to cover with the Earth's atmosphere. So we'll be doing some exam questions next. Okay, if you do have any questions, please just pop them into either the chat or the Q&A. So these are the learning objectives that we covered with the Earth's atmosphere. I just thought we'd recap them, make sure everyone's happy with them. So we started off by understanding the theories behind how the Earth's atmosphere developed. So hopefully you remember we talked about how volcanoes erupted and produced the main gases in the Earth's atmosphere today. And when they produced them, there was mainly carbon dioxide in the early atmosphere, but today, as we discovered earlier, the main gas is nitrogen, and carbon dioxide has gone right down to 0.04%. So we talked about the composition of the modern atmosphere, so I showed you a pie chart of that. We then went on to explain the greenhouse effect, which again, we've looked at again today, and I've shown you that diagram. We went on the impacts of global warming, which we covered in the quiz. So remember, sea levels rising, more stormy weather, ecosystems changing. So they're all impacts of global warming. And then we listed the ways to reduce greenhouse gas emissions. So some of you came up with those in the quiz today. So we went over kind of having a vegan diet, using renewable energy sources, biofuels, cutting down fossil fuel usage. All of these will try to reduce greenhouse gas emissions. And there was also the things like carbon capture and storage. So any carbon dioxide that is produced when we burn fossil fuels can be captured essentially and run underground to dissolve in rocks underground so that we stop it from going into the atmosphere. And then today we've looked at all the harms of the atmospheric pollutants and how they are produced. So that's kind of the main topic of the Earth's atmosphere and all the learning objectives we've looked at. So let's do a couple of exam questions then to consolidate this topic. Oops, not there. Okay, so how did the formation of coal decrease the amount of carbon dioxide in the Earth's early atmosphere? So I know this question says use the information above, but the information above doesn't really help you to answer these questions. So how did the formation of coal decrease the amount of carbon dioxide in the Earth's early atmosphere? So there are lots of answers for this. The pH of acid rain, so it's sulfuric acid, so it's about 3 or 4. So what did coal do? What happened when coal was produced? What specifically happened that reduced carbon dioxide in the Earth's atmosphere? Or you can completely ignore the first part and just tell me how the amount of carbon dioxide in the Earth's atmosphere has decreased, because that is still answering the question. I'll explain why in a second. So what caused the carbon dioxide in the atmosphere to reduce from the early atmosphere to the modern atmosphere? Yep, so someone is saying photosynthesis. Excellent. And so what happened was, you'll remember that when plants were produced, because of the fact that we had oxygen in the atmosphere and photosynthesis occurring, they reduced carbon dioxide from the atmosphere. And when they reduced carbon dioxide from the atmosphere, they produced oxygen. Now, the reason that photosynthesis is an answer for this question is because coal is formed from plants. So you'll remember last week we went over how the how the fossil fuels are produced. And coal is one of the fossil fuels that's produced by plants being buried in under lots and lots of rock. And when they're buried under lots of rock under high pressures, coal is produced. So the formation of coal came from plants. So you can talk about photosynthesis, reducing the amount of carbon dioxide in the Earth's early atmosphere, You can talk about plants dying. You can also talk about how someone is saying the carbon dioxide was stored inside coal. Excellent. Yep. So remember that coal is essentially a carbon compound. So yep. So you can talk about carbon dioxide being stored in coal as well. Okay. How does burning coal affect the amount of carbon dioxide in the Earth's atmosphere? How does burning coal affect the amount of carbon dioxide in the Earth's in the Earth's atmosphere? Any ideas? What does burning coal do? Good. Yep. So I've got lots of answers coming through. Great. So a model answer to this question would be that it actually increases the amount of carbon dioxide being released because trapped carbon dioxide is released from the coal. Yep. Good. So when we burn coal, carbon dioxide is released. So the fossil fuel reacts with oxygen to produce carbon dioxide. So that trapped carbon dioxide is released. Well done. Good. So for question here, this one, you can talk about photosynthesis, you can talk about plants dying, you can talk about the carbon dioxide being stored in the coal. Any of those answers would have given you the mark there. Excellent. Well done, everyone. Okay. So describe in as much detail as you can the reactions which take place at X, which is over here, and Y. So it says the amount of carbon dioxide in the atmosphere is increased by reactions that occur in internal combustion engines and is decreased by reactions in seawater. So what's happening at X? What's happening at X? Good, so someone's given me the process that's occurring. So Y then, does that increase? So it says, good, yep. Someone's saying carbon in the fuel is being oxidized. Excellent. So at X, combustion is taking place. Really good. And so you're burning your fuels and carbon dioxide is released from burning fossil fuels. Excellent. Really good job. Good. So someone is talking about nitrogen oxides. So this question is specifically asking about carbon dioxide. So I wouldn't talk about any of the other atmospheric pollutants. Good. Okay, what about at Y? So at X, we've got combustion taking place. When combustion takes place, that we burn fossil fuels in plenty of oxygen, which produces carbon dioxide, and that's released into the atmosphere. What about at Y? What's occurring? Good. So there are two things you can talk about with the C. So first of all, hopefully you remember that carbon dioxide does dissolve in oceans. And when it dissolves in oceans, essentially what's happening is it's reacting with metal oxides in the ocean to produce metal carbonates. So there's a lot of limestone in the oceans, and that's what this sediment here is. It's limestone produced from carbon dioxide reacting with calcium oxide to produce calcium carbonate. And what about if we think about plants in the sea? What do? Carbon dioxide, what happens to plants in the sea? Yeah, someone said photosynthesis. Excellent. So any carbon dioxide that dissolves in the ocean, if there are plants in there, they will take in that carbon dioxide to carry out photosynthesis. So there are two things you can talk about at Y. You can talk about the carbon dioxide being dissolved and that reacting with metal oxides to produce carbonate rocks. And again, they store that carbon dioxide, or you can talk about carbon dioxide being used in photosynthesis by aquatic plants. Excellent. Well done, everyone. Okay, so complete the sentence by putting a cross in the box next to your answer. So what's the percentage of carbon dioxide in the Earth's atmosphere today? So I've already mentioned this in today's webinar. Good, so I'll wait for a couple more people to answer. Everyone that has answered so far is correct. Good, it's less than 0.5%, so it's D. Not C, it's D. So it's the actual answer is 0.04%. So it's D. The percentage of carbon dioxide in the Earth's atmosphere today is less than in the Earth's early atmosphere. So we won't answer this question because we've done it already, but it's essentially saying that photosynthesis took in carbon dioxide, and as well as that, it was dissolved in oceans to produce calcium carbonate rocks. All of that will reduce the amount of carbon dioxide in the Earth's early atmosphere. Okay, let's have a go at this question though. So carbon dioxide and other gases in the atmosphere help to keep the Earth warm. Why do these gases help keep the Earth warm? Yep, so it's a 1 mark question, so you don't need to say too much. Good. So I've had a couple of answers, all correct so far. I'll wait for a few more. Good. So this question here is actually painting greenhouse gases in a good light. And I should say that a few greenhouse gases in the atmosphere are good because we don't want all of the energy from the Earth to be radiated into space, because otherwise the Earth would be really cold. So we do need a few greenhouse gases, but obviously in the Earth's current climate, there are too many greenhouse gases, and that's what's causing the Earth to warm up excessively. So this is just asking, how do these gases keep the Earth warm? So someone has said the greenhouse effect. So the greenhouse effect isn't quite correct because, again, as I said, this is talking about the positive of it. So what you can say that someone has said is they absorb infrared radiation emitted by the Earth originally from the sun to heat it up. That would be good. Yep, so it reflects any infrared radiation absorbed. So any of those would be good. So essentially they absorb energy from infrared energy radiated from the Earth and re-reflect it back down to the Earth. What's the test for oxygen gas? So we did this 2 weeks ago, I think. Good, yep, so it relights a glowing splint. It relights a glowing splint. Excellent, well done. So this is one of the kind of typical questions about atmospheric pollutants. So in the future, more coal-fired and fewer oil-fired power stations will be used to generate electricity. When coal and oil are burned, they produce the same types of emissions which can cause environmental problems. Emissions from the chimney can cause acid rain, global dimming, and global warming. Draw one straight line from each possible environmental problem to the emission that causes it. So, which emission causes acid rain? Which one causes acid rain? Good, sulfur dioxide. So sulfur dioxide causes acid rain. Which emission causes global warming? Good, carbon dioxide. And finally, which emission causes global dimming? Yep, carbon particles. So you could have also got the answer for saying that water vapor causes global warming, because water vapor is a greenhouse gas. Good, well done. Okay, so that's it for the exam questions on this whole topic. So hopefully all of you feel a little bit more confident with the Earth's atmosphere now. If you do still feel a little bit unsure, we have covered all the content, so you can always go back over the webinars and have a go. Also, there are lots of exam questions online that you can have a go at. So hopefully they will be helpful as well. Oh, not there. Okay, so let's go to the reactivity series then. So in the last kind of 15-20 minutes of the webinar, we're going to look at the reactivity series and how it's formed. So we've mentioned the reactivity series before. I know a lot of people have come up with mnemonics to help them to remember the reactivity series, and we've had loads of those before as well, which I definitely recommend. Water vapor is a greenhouse gas. That's why it leads to global warming. So it carries out the greenhouse effect. So a list showing metals in order of decreasing reactivity from top to the bottom. So that's what the reactivity series is. So potassium's the most reactive and platinum's the least reactive. And we use this when we're thinking about displacement reactions, which I said we'll look at tomorrow. But today we're specifically looking at, well, how did this list get formed? And that's what you need to know for your exams. So essentially, to form that list, scientists carried out two types of reactions. They reacted all of the metals with water, and they reacted all of the metals with acid. And they used these to show which ones were the most reactive and which ones were the least reactive. And we're going to watch a few videos on that in just a second. But before we do that, let's go through what happened so that we can understand what we're going to see in the video. So we said that potassium is the most reactive, and it goes potassium, sodium, calcium. All three of these metals, when we add them to cold water, they fizz and they are very, very reactive. And what will happen is when they react with that water, they will leave a metal hydroxide. So what that means is that potassium will react with water to produce potassium hydroxide, calcium will react with water to produce calcium hydroxide. And hopefully you remember that hydroxide ions make a solution alkaline, whereas hydrogen ions make it acidic. So because hydroxide is there, we get an alkaline solution. So those three metals will all react very vigorously with water. And then if we add acid to these metals, they tend to also react very rapidly. So potassium and sodium will explode when we add them to acid, so we don't tend to do that at school. And calcium will be very rapid when we react it with acid. If we go down to magnesium, aluminium, and zinc, so magnesium tends to have quite a slow reaction with water. It will react, but it will be very, very slow. But if we use hot water or steam, which is essentially hot water as a gas, then the reaction will be very quick. When we react magnesium with acid, it's really rapid. Aluminium and zinc will also have rapid reactions with acid, but aluminium and zinc will almost not really have a reaction with cold water, but they will be quick with steam. So hopefully you can see a trend. So what's going on as we go down the reactivity series is that it starts off with cold water being very reactive with the first few metals. And then as we go down, cold water becomes less and less reactive, but steam is the most reactive until we get down to platinum, gold, silver, and copper, which will have no reaction even with steam. So these metals are unreactive even with steam. So you don't need to learn these reactions by heart. You need to know what they produce, which we're going to go through in a second, but you don't need to know what happens. This is just to show you what we expect and how they form the reactivity series. So they did these reactions to show that potassium must be really reactive, because when we react it with water, you get this very rapid reaction. But for example, platinum will have no reaction with water, even when we heat that water up, which means that it's very unreactive. So it's about just being able to describe that trend. And it's the same with acid. So we start with, obviously we react it with dilute acid. We start with potassium, which will explode with that acid. Magnesium, aluminium, and zinc will have rapid reactions with acid. And as we go down, further down, we start to get no reaction, even with warm acid. So we don't tend to use warm acid, but this is just to show that if we did add warm acid, it will speed the reaction up, which we expect. So we looked at particle theory and what that does and the kinetics of reactions. So we know that if we heat things up, they tend to react faster. Iron, when we react it with water, tends to rust slowly. So we've looked at rusting before, but it will rust slowly. So any questions on those reactions? We're going to watch some videos now, which will hopefully show that. So lithium is not there. It's because it's not actually in the reactivity series that you need to know, but we can predict where it goes. So it's a very good question. So lithium is in group 1, and hopefully you remember group 1 goes lithium, sodium, potassium. Now, if we have a look on the reactivity series, potassium is first, followed by sodium. And the reason for that is, if you remember when we went through group 1 elements, the reactivity actually increases down the group. So they become more reactive down the group. And does anyone remember why? Why does reactivity increase down group 1 elements? Yep, so someone has said it's easier to take away that electron. So remember, they all have 1 electron in their outer shell. Good. So the reason that the reactivity of group 1 elements increases down the group is because as we go down the group, the elements get bigger. And essentially, the 1 electron that they've got in their outer shell becomes further away from the positive nucleus. So that 1 electron that's negatively charged becomes less reactive. Becomes less reactive with the positive element. The positive nucleus, sorry. So that negative electron reacts less with that positive nucleus. So that's one reason. So as they get bigger, the electron is further away from the nucleus. The other reason is shielding. So someone has said that there's less shielding as we go down the group. There's actually more shielding. So what happens is the outer electrons, because they are further from the nucleus, any shells that are in between the nucleus and the electron they provide a shielding effect. And that shielding effect essentially blocks the positive charge of the nucleus from the outer electron. So as we go down the group, the reactivity increases. So lithium, we would expect to be around here and around here. And the reason it's not in the reactivity series, as someone said, it's not a common metal that's used in school laboratories. So we tend to only have the reactivity series, including these metals. So let's watch some videos, which will hopefully make a bit more sense. So we'll start off by watching reactions with water. So okay, so what we've got going on is we've got some water over here, and the scientist is just adding some phenolphthalein indicator. So you'll remember that that indicator tends to go purple when you've got an alkaline solution. So that's why we've added it, because remember that our metals will react to produce a metal hydroxide. So we're expecting it to go purple in the reactions that take place. Okay, so first of all, he's adding it to tin. So SN is tin. And again, tin is there in the reactivity series, and you'll see it says a slight reaction with steam. This is cold water, so we're not expecting much of a reaction. Iron, again, not expecting a reaction. We are expecting a little bit of a reaction with magnesium. So hopefully you can see that metal is starting to go a bit purple. Copper is down here. We're not expecting a reaction even with steam. So this is cold water. Going to add it to zinc. Again, zinc, very slow or no reaction with cold water. Watch calcium, because we're expecting a very fast reaction. So there you go. That's the very fast reaction of calcium reacting with water. You can see that's gone bright pink, and that's because of the calcium hydroxide, and it's about to overflow as well. So you can see that. So that's calcium hydroxide that's making the indicator go pink. And if you also have a look at magnesium, you can see that's also starting to become pink, and that's magnesium hydroxide that's making that indicator go pink. So hopefully that made sense. So that's the reactions with water. So tin will not really react with cold water. So tin on our diagram is over here. So it will react with steam very slightly, but this is cold water. Iron tends to rust very slowly. So if we left that for days, it will probably react. Magnesium's got a bit of a slow reaction, but it does react. Copper will not react. Zinc, very slow or no reaction with cold water. And calcium has a very fast reaction, which we saw. Okay, let's have a look with acids. So same metals. So we're going to add acid to each of these. So with tin, again, we're not expecting much of a reaction at all. And you can see there's no effervescence. There's not really any reaction going on. Same with iron. We're not really expecting any reaction. Okay, magnesium, we are expecting a reaction. So watch magnesium. So now, so hopefully you'll be able to see, there you go. So you've got some effervescence going on there. It's quite a vigorous reaction. Copper, we're not expecting a reaction at all. So you can see that. So if you look at tin, iron and copper, there's no reaction going on. Zinc, we are expecting a reaction. And if we have a look, that reaction is taking place, but it's less vigorous than magnesium. So there is effervescence there, but it's less vigorous than magnesium. So we can see that then zinc must be lower. But now look at calcium. So we're expecting this to have a very, very vigorous reaction. If you have a look, there you go. Again, it's a really vigorous reaction, much more vigorous than magnesium. And much more vigorous than zinc. So you can see again, that's overflowing there. Okay, so as I said, those are the reactions that we do to have a look at where the metals lie in the reactivity series. I can put those links into the chat if you would like to watch them through again. If not, you can just type into YouTube these reactions, so metals reacting with water and metals reacting with acid, to have a look at the reactivity series. So the next thing that we're just going to cover today then is the actual equations of what's occurring. You can watch sodium with acid, but it would explode. So I'm not sure if there are any videos on there. You don't tend to do it at school. If you do, your teachers will tend to do it for you, but it's an explosive reaction. So first of all, we started by watching reactions with water. And as I said, when we react our metals with water, a hydroxide is produced. So we had aluminium reacting with water, which produces aluminium hydroxide. So if we wrote out that reaction, we would have aluminium, which is Al, plus water, producing aluminium hydroxide. So aluminium is in group 3, it produces a 3+ ion. Hydroxide is OH-. So what's the formula for aluminium hydroxide? Does anyone know what's the formula for aluminium hydroxide? Good, I've had one answer that's correct. If anyone else wants to have a go. Aluminium hydroxide, so Al3+ and OH-, how do we, when they react, what's the formula for that compound? Good, excellent, okay, everyone's giving me the correct answer there. So it's AlOH3. So the way I always do it is I swap the charges. So what I mean by that is hydroxide is essentially a -1 charge and aluminium is a 3+ charge. So that means if we swap the charges, aluminium becomes 1 and hydroxide becomes 3. The other way you can think about it is if you think about the ionic bonding that's occurring, aluminium has lost 3 electrons and hydroxide has gained 1. For aluminium to have its full outer shell, it needs to gain 3 electrons. So to gain 3 electrons, hydroxide only has 1 to donate. So that means we need 3 hydroxide ions to make the aluminium a full outer shell. So it becomes aluminium hydroxide like so. So aluminium hydroxide, and then we get hydrogen produced, which is H2. And we can have a go at balancing that equation. So if we have a look, we've got 3 hydrogens plus 2 hydrogens, which makes 5. So remember, we always want it to be even. So we can start off by maybe putting a 2 here. And if we do that, then we know that our hydrogens have become 6 plus 2, which is 8. So we put a 2 here in front of the aluminium. But then if we have a look at our oxygens, it won't work because it won't match with the hydrogens. So if we have a look, we have 2 oxygens times 3, which is 6. So that means that over here, we would have to put a 6. And now we have 12 hydrogens, but we don't have 12 hydrogens. So let's have a look. We've now got 2 times 3, which is 6, plus 2, which is 8. So we just need to make these hydrogens match. So what does the hydrogen have to become for it to match? Does anyone know? What does the hydrogen, what do we need to put in front of that hydrogen for the balanced equation to match? Good, yep, 3, excellent, well done, 3. Oh. Excellent, okay, and I won't go through the other 2 reactions with water, but they're essentially exactly the same. So sodium hydroxide is NaOH, so you can have a go at doing these on your own, plus hydrogen, and potassium hydroxide is KOH. So reactions with steam are a little bit different because with steam, we get oxides produced instead of hydroxide. So steam is just hot water. So if we did magnesium plus steam, we do Mg, which is magnesium. Steam is just water, but as a gas. So I haven't been putting the state symbols in, but aluminium would be solid, water would be liquid, aluminium hydroxide would be aqueous, and hydrogen would be a gas. So solid, liquid, aqueous, and gas. So magnesium is a solid plus water, which would be as a gas here because it's steam, produces magnesium oxide. So magnesium oxide, Mg2 plus, and oxygen produces an O2 minus. So what's magnesium oxide? What's the formula for magnesium oxide? MgO. Yeah, so steam is actually water vapor. It's very hot water. Good, so it's MgO. So we get MgO produced, magnesium oxide, plus hydrogen. And if you have a look, that's already balanced. There's 2 hydrogens, 1 oxygen, 1 magnesium, 1 magnesium. And it's exactly the same with the others. So I'll just tell you, if you do want to have a go at these on your own, lead produces a Pb2 plus charge. So that should help you to be able to write the formula for lead oxide. Then finally, the reactions with acid. So we saw zinc and tin reacting with acid in the video that we watched. So if we do the one for zinc, zinc is Zn. Acid, hydrochloric acid is just HCl. Remember, acids are always aqueous. It's going to produce zinc chloride. So zinc chloride. So what's zinc chloride then? If I tell you that zinc forms a Zn2 plus charge, Zn2 plus, and chloride is Cl minus. So Zn2 plus, Cl minus. What's zinc chloride as the formula for that? Good, ZnCl2, excellent, well done everyone. ZnCl2, zinc chloride plus hydrogen. So have a go at balancing that. Anyone want to tell me what do we need to balance? I'll give you a clue, there's only one thing that needs to be changed. Good, yeah, excellent. So 2HCl, really well done. 2HCl, and that's the fully balanced equation for zinc reacting with hydrochloric acid. So these are the reactions that we saw take place. We didn't see the reactions with steam, but what I'm pointing out here is that when we react with steam, instead of producing a hydroxide, we produce an oxide. And when we react with water, we produce a hydroxide. And when we react with acid, which is usually dilute hydrochloric acid, we produce a chloride plus hydrogen. So the only thing kind of unifying all of these 3 reactions is that hydrogen is produced. So hopefully that's helped you to understand the reactivity series a little bit and how it's formed. Tomorrow we'll be looking at the displacement reactions. So that's the other way that we form the reactivity series. And we'll go into displacement reactions and how to write those out and how to understand what's formed. Someone's asking, what does the CO2 react with under the oceans? It reacts with metal oxides to produce carbonates. Excellent. Lots of people answering the questions on the equations, which is really great. Is there any rule for the reactions that we can find in the periodic table? Not really. So a lot of the reactions that you'll learn over the course of your GCSE curriculum are repeated. So these reactions here, they're repeated from when we looked at, for example, group 1 metals. So when we looked at the group 1 metals, we looked at the reactions with water and we looked at the reactions with acid. So this is just repeated from when we looked at group 1 metals. So usually there is a lot of overlap, and it's just about, as someone has just said, actually, you know the reactivity through their position. So yeah, that's a really good point. So that reactivity tells you about the reactivity series, but also just when you're learning reactions and things, you'll see them pop up again. So it's important not to kind of not to feel overwhelmed by the number of reactions that you need to know, but instead try and see the similarities between them, and try and make links. That's what I always do. If you can form links between them, you're more likely to remember them. So I remember these reactions by remembering that all of them produce hydrogen. And then I remember that water, if you have a think about what's produced, in water there's H2O. So that means that the hydrogen's taken away, so we're left with oxygen. And if aluminium reacts with the oxygen and potentially one other hydrogen, there's aluminium hydroxide produced. So I know we always form an alkaline solution here. With steam, there tends to be less hydrogen there, so we tend to have oxides produced. And when we react with acid, again, we're going to produce hydrogen and we're going to produce salt with the acid in it. Someone's asking, are we going to go over these when we go over the reactions of acids? I think we've already gone over the reactions of acids. So this is just a snippet of this topic because I know that some people were asking about it, but I think we've already gone over the reactions of acids. So have a look over previous webinars. Okay, great. Have a lovely rest of the day today, everyone, and I will see you on Wednesday morning where we'll look at displacement reactions and the Earth's resources, which is the next topic for the Earth that we'll cover once we've gone over displacement reactions. Okay, take care, everyone. Bye.